Hello, my name is Shubhadeep Pundal. In this short video, I'll outline my research interests which sit at the intersection of quantum algorithms, machine learning, signal processing viewed from a computer science and machine learning perspective. My primary research direction is the use of quantum algorithms as computational subroutines rather than complete replacement of classical methods. So, in particular, I study how well defined quantum subroutines such as quantum Fourier transformation, quantum phase estimation, and HHL algorithms can be integrated in the existing classical algorithms and signal processing algorithms and machine learning methods to avail the advantage of promised quantum speedups. So, in these settings, quantum routine act as specialized computational primitives, for example, accelerated spectral estimation and phase extraction and structured matrix operation. So the main emphasis is actually on finding structured problems well suited for quantum computing methods. So the viewpoint is to keep the research grounded in algorithms, complexity analysis, and system level integration, which are core concerns in the computer science and engineering. A second major direction of research focuses on learning quantum states and quantum channels directly from data. So quantum systems are very difficult to characterize because measurements are noisy and data is very much limited. Instead of using brute force constructions, I develop learning-based inference methods that treat quantum system identification as a data-driven estimation problem. In this regard, I solve particular two problems. The first problem is quantum state tomography, where we actually learn the quantum state from the data, and the second problem is quantum channel learning, which is learning the quantum process or quantum dynamics from the data. In this regard, I actually use Bayesian inference and quantum neural networks to build models that are statistically sound, noise-hour, and physically consistent. Another important direction of my work is quantum machine learning on near-term noisy quantum devices, often referred to as NISQ devices. My work focuses on variational quantum circuits or VQC as trainable quantum models. These circuits are conceptually similar to neural networks. They use parameterized quantum gates that are optimized during data-driven objectives. So, however, unlike classical models, VQC must operate under strict hardware constraints. So, these hardware constraints are circuit depth, connectivity, and hardware noise. So, I design the VQC architecture that balance expressibility and trainability with an emphasis on model that can realistically execute it on classical quantum hardware. Rather than abstract expressibility, my focus is on practical circuit design and stable optimization. A central theme of my work is also hardware aware and noise robust training, because whenever you are designing some algorithm for a variational quantum circuit and quantum machine learning type of architecture, it should have a particular low depth architecture for next enabled devices. I explicitly account for device constraints such as native quantum gate sets and limited connectivity, and develop training strategies that mitigate noise, barren plateau, and gradient instability. Finally, all these things gets together and it comes to hybrid quantum classical learning loops, because whenever you are talking about some quantum devices, you cannot operate it in isolations. All training is performed within a hybrid quantum classical loop. In this setting, quantum hardware is used to evaluate parameterized circuits and measure observables, while classical processor handles the optimization and parameter updates. So that is a control type of task for quantum hardware. So my work studies how the whole information for a data-driven objective flows through the quantum and classical boundary, and how classical optimization strategies can be adapted to compensate for noisy quantum measurements. Apart from this, I also work on quantum-inspired machine learning, where we borrow mathematical structures originally developed in quantum physics, such as tensor networks, to design efficient learning algorithms that can entirely be executed on classical hardware. These methods do not require any quantum computer. Instead, they exploit concepts like entanglement, low-rank structure, tensor factorization to present and process high-dimensional data more efficiently than existing conventional architectures. Besides this, also, this particular quantum-inspired methods has particular two key purposes. One of them, they act as a strong classical baseline, ensuring that any claimed quantum advantage is meaningful. And secondly, they provide theoretical insight why such quantum advantage is coming from using a quantum algorithm. So the direction is actually to bridge classical machine learning algorithm, quantum algorithm, and complexity analysis theoretically, and using the quantum-inspired architectures. Finally, I will summarize what is my research direction. So in the end, I will have to say that I work in the intersection of signal processing and machine learning formulation, with quantum computation being used as a targeted and algorithmic subroutine. And as my background is wireless communication and networks, most of my invented algorithms has been deployed in the classical signal processing and wireless communication pipelines. Thank you.